Howdy, folks. So we're going to be looking at the Compton effect, which is another sort of support of light acting in a particle way. But just want to point out that one of the things you have to feel comfortable about to be looking at this thing called the Compton effect is good old-fashioned 2D conservation of momentum problems. So if that's something you need to go back and review, so be it, because that is where you have to be strong first. But as long as you've done that, let's continue into this. So where we're at is a point where Einstein and other physicists, they're all kind of playing around with all these ideas that they've got, that light has these particle-like characteristics. And one thing that comes out of all of this is light should have a kind of unexpected characteristic. It should actually have momentum. Now, that's kind of weird because EMR itself, by definition, is massless. So the photons are massless. But there was still this idea that because of the way they were interacting in the photoelectric effect, that they would also somehow have this momentum quantity also. So out of all of the theoretical work that they were doing, they came up with a formula for it. P equals h over lambda, and then if you do want to use the universal wave equation, you can substitute that in and get P equals hf over c. Now, the first formula written there is on your data sheet, and if you ever needed to, you could just use universal wave equation to flip around a frequency into a wavelength and keep using it even that way. But what we see here is kind of that weird duality of wave-particle duality. We're measuring momentum, which is a very particle matter characteristic. And how are we doing it? We're using wavelength, the most wavy measurement that you can possibly do. So it's really kind of weird that way. Anyways, in the formula, P is still classic momentum, and it even still has the same units, kilogram meters per second squared. Although, technically, remember, we can use the units Newton seconds also, but we use that more often when we're doing impulse, not momentum. But still, it's an option out there. We're using classic Planck's constant. And that's kind of with that argument that we have of we have to have a reason to use the other version of Planck's constant, and we don't here. We want something that does use compatibility with all of physics formulas. That's kind of important. Wavelength, classic in meters, if we use frequency in hertz, and c, of course, the speed of light. Now, out of all of this stuff, they do also have another formula that just kind of pops out, E equals PC. Now, that formula is on your data sheet also, and I will say we don't use it nearly as often, but there's just something kind of neat that I want to sketch over here for you, just so you can see there's something kind of cool about this. There's something hidden as sort of a look into the future prize. If we think of classically what P is equal to, it's P equals mv, classic momentum. Now, if we are talking about doing all of this stuff, though, we wouldn't be using v, we would be using c for the speed of light, because it's not just any velocity. So look at what happens when we substitute that in. We get mc times c. This formula isn't just for kicks. It's there for a reason, and it is based on a lot of stuff beyond even directly Einstein's special theory of relativity. So we have to understand the significance of E equals mc squared is built into a lot of the physics we're looking at right now. Anyways, continuing right along. Oh, I gotta get out of this pen mode. I think I need to get out of this pen mode. There we go. Oh, and I guess it also helps if I can get rid of all of that stuff. Anyways, there's this guy named Compton, and what he's playing with is an idea that isn't really all about him trying to do anything to do with wave-particle duality. Instead, what he wakes up in the morning kind of asking is, oh, I wonder what happens if. And his I wonder what happens if is based on looking at a relatively standard kind of idea. It's just how he's going to look at it is a little bit different, because he wants to ask the question of, what do waves do when they interact with metalloids? And remember, metalloids are anything along the sort of the edge of the staircase of the periodic table, where we have metal and non-medical characteristics. And he's kind of wondering, if I shoot something like X-rays at a metalloid, and in the diagram here you can see that he chose graphite, he's asking himself, will this be able to pass through? Will it block the X-rays, sort of like thick metals like lead will do or something like that? Or will it pass right through like nobody's business? Well, he does have a little bit of a prediction. He basically assumes that when the incident X-rays hit the graphite, they will come out the other side. But in his prediction of things, he believes that fundamentally they will squish a little bit. Now, I am not saying this is the same thing, but it's kind of like when we talked about polarization of light, that when it hit, it kind of squished in one dimension. Kind of think of this as the waves are traveling to the right, and when they smack into the graphite, it squishes them a bit. They still get through, but it's changed their wavelength. They're now smaller wavelengths. Now, the way that Compton is explaining this in his initial assumption, his hypothesis, is the X-rays that we started with, no big surprise, are called incident X-rays, and the ones that did pass through are the transmitted X-rays. That's his theory. Does it actually stand up with what he observes? No. He sees something really weird. First of all, the X-rays don't even go straight through, they are scattered at an angle. Now, it's important we remember that name, because it's what we're supposed to say when we're talking about this sort of an effect, okay? That they, and this is not a refraction thing, because the incident X-rays can come in perpendicular to the graphite, which means that there shouldn't be any refraction anyways. This is a scattered X-ray. And so one other thing that we're going to have to kind of use in our vocabulary in a moment is the incident X-ray is the initial one, and the scattered X-ray is the final X-ray. Kind of keep that in mind, because it's going to work with some stuff we're doing here. But the other thing he notices is the X-rays have longer wavelengths. Now, sure, the scattering, okay, maybe something else is happening here, but the wavelength got bigger? How could that possibly happen? It should squish. So he starts working back, looking at all of this work, that's been done over years and years and years, and he comes across all this stuff about, hey, what if light could have momentum? So he starts kind of thinking about it and realizes that the waves that have a longer wavelength, the scattered X-rays, according to P equals h over lambda, where bigger wavelength means smaller momentum, it makes it sound like the X-rays, when they hit the graphite, they lost some of their momentum, because after the collision with a longer wavelength, they have less momentum than they started with. Well, how would that happen? Because they collided with something, and they did a regular 2D conservation of momentum thing. So Compton starts looking for where would the other thing be? Well, it's got to be kind of going down and to the right, because if we think of the classic 2D collisions that we did way back, sort of the the most basic ones that would do sort of those Y shapes of one ball hitting another one off center, and then they'd split off in kind of a Y shape. That's what this kind of looks like. So he starts looking, at least in this diagram, the way it's drawn, in the bottom right, and he discovers that there are ejected electrons, and they're shooting off at very specific velocities. And when he starts doing all the number crunching, what he finds is that if you do all the calculations, the X-rays, you have to do their momentum using P equals h over lambda. And for the ejected electron, well, it's a standard good old-fashioned thing. So you do P equals mv for it, and you take into account all the angles and all that sort of stuff. It is perfect 2D conservation of momentum. And we actually can't exaggerate using the word perfect here, because when he did the calculations, he found, because, if you think back to, even if some of you did the conservation of momentum lab, you did not get exact results at all. There was momentum lost. And in most experiments we do, stuff like that happens. And yet here, when Compton does it, like pretty much as many decimal places in as he can go with SIGDIGs, the momentum is perfectly conserved. What we're kind of seeing is that although in our macroscopic world, 2D collision momentum questions actually don't work out that perfectly, down at the quantum level, it is essentially perfect. So, if these electrons are being thrown off at an angle like that, he realizes that he's looking at something pretty important here, because it's proof that the photons coming in definitely have a momentum characteristic because of the way they're interacting with the electrons. So, hey, he gets to name it after himself, and he calls it the Compton Effect. Although sometimes you might also hear it referred to as Compton Scattering. I've heard different arguments on this, that if you say Compton Scattering, you're talking more about the scattered X-ray, for example, but it can refer to the whole thing also. But essentially what we're seeing is two aspects at the same time. We're seeing our wave-particle duality, the photon theory of light, where even though we're, like I'm saying, using wavelength to calculate the momentum, we're using a wave characteristic to measure a particle characteristic. We're looking at wave-particle duality in the momentum of these photons. And then we're also using classic conservation of momentum in order to be able to do our calculations. Keep that in mind, because those are the two main physics principles that if you were doing a question like this on a diploma, those are the two physics principles you'd have to give for how you're solving this. Now, the question I sometimes get asked at this point, or around this point, is, but haven't we seen this before? Isn't this just the photoelectric effect? No, it is not. And again, this is where we have to really see that there are differences, so that we know if we're asked questions about it, we can give that set of reasons that the photoelectric effect is one thing and the Compton effect is something different, even if it's kind of the same-ish. So in the photoelectric effect, we're shooting high-frequency EMR at metals. But in the Compton effect, we're shooting high-frequency EMR at specifically non-metals, because we're going to count the metalloids as non-metals. In the photoelectric effect, the incident EMR photons hit the metal surface, and in the act of interacting with the valence electrons, that EMR photon is destroyed. It ceases to exist because the very energy of its existence is transferred to the electron to snap it off and give it kinetic energy to fly away. In the Compton effect, the photon is not destroyed. In fact, it continues on its merry way. All that it's done is lost some of its momentum. And that again kind of comes into the last things we can talk about here. In the photoelectric effect, we rely on conservation of energy, because we have incoming energy from the photon becomes the work function of snapping off the electron plus the kinetic energy of the electron shooting away. In the Compton effect, we only look at momentum. We're purely doing conservation of momentum work, nothing to do with energy. So keep these ideas separate in your head. They are different aspects of quantum mechanics, and they have to be recognized as separate. So, What else can we do with all of this? Well, Compton and others after him start doing all these great things with calculations and formulas and looking at situations where they reproduce this again and again, and not just with X-rays. You can also do it with like gamma rays and stuff like that. It's just that sometimes the angles get really kind of wonky and stuff. Anyways, they come up with this idea that you can actually predict, purely based on the angles, how the incoming wavelength, the incident X-ray, for example, becomes a different wavelength for the scattered X-ray. Now remember I said to you the incident X-ray is our initial and the scattered is our final. Final minus initial, that's delta lambda. So that's what this formula lets us do. It lets us calculate the change in the wavelength between the incident and scattered wavelengths. So on the left-hand side of this formula, if I wanted to, that delta lambda could be replaced with lambda scattered minus lambda initial. Because remember, we're treating the scattered as though it is a final. H is regular Planck's constant, so it's just a constant. M is the mass of the electron. That's not going to change. C is the speed of light. That's not going to change. That whole sort of H over MC thing there, it's actually a constant. And then it multiplies by 1 minus cos theta. Theta, that's what we've got to put in. We've got to look, I'm just going to jump back here for a second. We'd have to look at where the incident X-ray was initially going straight across, and we would measure from that initial straight across to the right path the angle that the X-ray has scattered at. So, I give as an example, we have an X-ray light source that has a wavelength of 1.28 times 10 to the negative 12 meters. That's got to be our incident wavelength because it's the X-ray light source. It's what we're going to be shining onto the graphite. And it says we shot that at a piece of graphite. On the other side, the X-ray is observed to have a scattering at an angle of 15 degrees away from the original path. Determine the wavelength of the scattered X-ray. And I'm telling you to ignore sig digs here. It's not a big deal. And then determine the velocity of the ejected electron. The first part is going to use that delta lambda formula. The second part, that's going to be a whole 2D conservation of momentum question. So here's a brief little sketch of what it would look like, showing the incident X-ray coming in and the scattered one in green going off at an angle of 15 degrees. And the electron, it's got to be going somewhere down to the right. The other thing is, please understand in this diagram, I chose not to keep drawing the X-rays as wiggly wavelengths, because to be honest, we're kind of thinking of them more as particles right here anyways. And also, I just wanted to make sure that you could see very definitely what the initial path was of the X-ray aimed straight in at the graphite and the angle of the scattered X-ray. So we'll grab this formula for starters and we get ready to start throwing in all of our numbers and everything like that. Basically, like I said, the H over MC part is just going to be a set of constants. The only thing I really had to put in here was that 15 degrees. What I would suggest is do all of the stuff outside of the brackets first. It's really just a bunch of constants anyways. Excuse me. And then take that, multiply it by the, in brackets, 1 minus cos 15, and get your answer from there. If you double check yourself, you should find, and right here, I'm not doing anything with sig digs with anything that I'm doing on this slide, 8.266072876 times 10 to the negative 14 meters. Now remember, that's not our scattered wavelength. That's our delta wavelength, how much it's changed. So if I want to figure out what the scattered wave is, I've got to think to myself, well, that's the delta lambda equals lambda scattered minus lambda initial, because delta anything is always final minus initial. I can take that and rearrange it to find the scattered wavelength. It means that I'm going to add lambda incident to both sides, And then I end up with lambda scattered equals delta lambda plus lambda incident. And if you even think of it, that's got to make sense, because we know that the scattered wavelength is bigger than the incident. So I'm taking the incident, I'm adding the delta, I'm going to get something bigger. So I'm taking my numbers that I've got for the delta lambda we just measured and the incident wavelength of the X-ray that we were given in the question. I'm adding them together, and I get 1.362660729 times 10 to the negative 12. Now, certainly, if this was the only question you're being asked, like on an exam or something, you'd go ahead, you'd round off for sig digs. Because of the angle, it really looks like I've only got 2 sig digs, so it'd be like 1.4 times 10 to the negative 12. But I told you here, just get the unrounded value, because I want to use this as we get into the 2D collision part of the question. So this is answering that first part that I was asked. And now we're going to move on to the second part, the let's find out the 2D collision part. So let's figure out the momentum of our two X-rays. For the incident X-ray, I've got P equals h over lambda, regular Planck's constant, divided by the incident wavelength. Nothing changed there. That's going right back to the very original number I was given for the incident wavelength X-ray. And I get a number, and I'm not going to do any rounding off because I'm about to do a bunch of 2D collision stuff. For the scattered X-ray, I do a similar calculation. This time I use the number that we just calculated on the previous slide for lambda scattered. So that's the number that's on the bottom of that equation. And I get 4.865 blah, 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 times 10 to the negative 22 kilogram meters per second. Both of these, you'll notice, are incredibly small momentums. And that's because we are dealing with wavelengths of light, photons of light, I should say. You don't feel photons of light banging into your head doing collisions, because on a macroscopic scale that we're on, this is insignificant. This is meaningless, even considering the storm of photons that are interacting with us. And all they're going to do is maybe be knocking off some electrons or something. They're not going to be ramming you down against the floor or something. Next part we're going to look at is thinking about how we did these questions way back when we were originally doing 2D collisions. The incident X-ray is our entire before the collision momentum. And, lucky for us in the diagram, it's all x-axis. So that means that I can take that momentum and just say, yep, that's total momentum at the beginning, it's everything, and it's all x. There is 0 y component. But for the scattered X-ray, which I know stuff about after the collision, it must have x and y components. So just like we would do back in 2D collision stuff, I'm going to figure out those components of the scattered X-ray. So I take my number with the angle, I draw myself a beautiful triangle, and I come up with an x component that I used cos to find, and a y component that I use sine to find. And yes, I could have, just like we talked about when we did 2D conservation of momentum, I could have done something like using tan, or I could have used Pythagoras, but remember, then I'm depending on numbers that have been through the meat grinder of my calculator more, and I don't trust them as much. But this gives me x and y components. First thing I want you just to notice is, do you see that x component is less than the x that I have from the incident X-ray? Yeah, that's because that's momentum that was given up to the electron. And I also have a y component, and that's pointing up. That must be cancelled by the y component of the electron. So, if we're going to figure out our components for our electron, we have the incident X-ray that was coming in and was all x. We have the scattered X-ray x component. We subtract them. The leftover little bit must be the electron's x component. Then I have the very easy task of saying, for the y component, if the scattered X-ray was all up y component, then it has to be equal but opposite y component on the electron. So that's my y component. So there are my components of my electron. And I should point out to you this, just because of how I was drawing it on the slide, it is very not drawn to scale, because that x component being 10 to the negative 23 would be super duper tiny small, and the y component times 10 to the negative 22 would actually be the bigger one of the bunch. What we quite often find is that, like, the electron in these collisions will scatter at a really big angle. That is not unexpected at all. So, if I have all those numbers, I can figure out the angle, I can figure out the hypotenuse, and because that is momentum, I can use that to figure out the velocity. So I first used tan with my triangle to figure out that, wow, it is going at a pretty big angle, 69.1 degrees below the original path of the incident X-ray. I used Pythagoras to put in those two components, and then I took that hypotenuse and I said, well, P equals mv, because the electron is a particle. Solve it for v, put in the momentum, divide by the mass, and you're going to get the velocity of the electron. Actually about half the speed of light. That is insanely fast. But that's what it's going to do after it got hit by that high energy X-ray that has lots and lots of momentum. Now, I do expect that you're probably going to want to go back and re-watch some of that video a little bit, maybe pause it a few times when you're looking at some of the numbers I'm crunching through. There are also a couple of questions you can try from the textbook. There's not a lot, though, and that's because actually coming up with Compton Effect questions where all the numbers actually balance out realistically for the way they would need to is actually pretty difficult. But take a look at that, and there is also a question that's on the quantum worksheet for this chapter. So good luck with all of that.